We want to use a triple integral to determine the volume of the solid bounded by the paraboloid given by f of x comma y and the plane z equals 0, which would be the xy plane. And for this example, we'll be using cylindrical coordinates to determine the volume. Let's first look at this graphically. So here we see the graph of the paraboloid in green and the plane z equals 0 in yellow. We're trying to find the volume of the solid below the paraboloid and above the xy plane, or the plane z equals 0. To find the volume, we need to evaluate this triple integral here, where we have the triple integral over the region D. Notice how the integrand function would just be 1, and the region D would be the solid region we're trying to find the volume of, and differential v in rectangular coordinates is equal to dz, dy, dx, or any of the 6 possible orders of integration, and in cylindrical coordinates, differential z is equal to r dz, dr, d theta. So because we're using cylindrical coordinates, we'll determine the volume by evaluating the triple integral over the region D of r dz, dr, d theta. So we first want to determine the limits of integration with respect to z. To do this, we need to express z in terms of r and theta, and also recognize that the solid region is bounded below by z equals 0 and bounded above by z equals 9 minus x squared minus y squared. So again, the solid region is bounded below by z equals 0, which will be our lower limit of integration for z. And then for the upper limit of integration, we would have z equals 9 minus x squared minus y squared, which must be written in terms of r and theta. So let's write this as z equals 9 minus the quantity x squared plus y squared. In this form, because x squared plus y squared is equal to r squared, we can write z as z equals 9 minus r squared. So now we have our limits of integration with respect to z. So we know the volume is equal to the triple integral. Again, we have r dz, dr, d theta. And now we know the limits of integration for z are from 0 to 9 minus r squared. And now to find the limits of integration for r and theta, we need to look at the xy trace. And we can find the xy trace by setting z equal to 0 in the equation for the paraboloid. So for the xy trace, again, we start with our equation of the paraboloid, set z equal to 0. And here, if we move the variable terms to the left side, we have x squared plus y squared equals 9, which we should recognize as this circle here, where it's centered at the origin, and the circle has a radius of 3. If we go back to our graph just for a moment, we can also view the xy trace by looking down on the xy plane, as we see here. And now we need to find the limits of integration for r and theta that would trace out this area in the xy plane. We'll notice how the radius r would be from r equals 0 to r equals 3. And limits of integration for theta would be from 0 all the way to 2 pi for one full rotation around the circle. So if we evaluate the triple integral, this will give us the volume of the solid bounded by the paraboloid and the plane z equals 0. Let's go and evaluate this on the next slide. So we first integrate with respect to z, treating r as a constant. So we're going to have r times z, or rz. And now we need to find big F of b minus big F of a. And we're making these substitutions for z. So we're going to have r times, and then when z is 9 minus r squared, we just have 9 minus r squared. And then, of course, when z is 0, we just have 0. So this gives us a double integral, where the integrand function is now going to be 9r minus r cubed. And now we integrate with respect to r. So we'd have 9 times r squared divided by 2, or 9 halves r squared, minus r to the 4th divided by 4, or 1/4 r to the fourth. Now again, we find big F of b minus big F of a. So when r is 3, we have 9/2 times 3 squared minus 1/4 times 3 to the fourth minus, notice when r is 0, both terms would be 0. And this expression here simplifies to 81/4. So now we have the integral from 0 to 2 pi of 81/4 integrated with respect to theta. So we have 81/4 theta. And now we find, again, big F of b minus big F of a. So when theta is 2 pi, we have 2 pi. When theta is 0, we have 0. So we have 81/4 times 2 pi, or 2 pi over 1. Simplifying, we get exactly 81 pi divided by 2, and this is volume, so this would be cubic units. So the volume is equal to 81 pi divided by 2 cubic units, which is a decimal, would be approximately 127.2345, again, cubic units. Which again would be the volume bounded by the paraboloid graphed in green and the plane graphed in yellow. I hope you found this helpful.